Good day, everyone. My name is Chichu Zheng. We are from ClusterTech and the University of Hong Kong. Our presentation is on the development of customized variable resolution CPAS for meteorological simulation. In addition to the posters on the EGU website, we have elaborated the content as a white paper on our website. I'll show later. If time allows, I shall show you the visualization of the data used in this piece of work. So the poster first. CPAS is the ClusterTech platform for atmospheric simulation. It is derived from NCA's MPAS model. On top of it, we have added two features: hierarchical time stepping and customizable unstructured mesh generation. We have generated a customized mesh which has 1 km resolution around Hong Kong here. Zooming in, this is a visualization of the mesh. And zoom out a little bit, the distribution of resolution is like this. So we have added regions of refinement that we think that will help the weather prediction in Hong Kong. So, and we have turned on a feature in CPAS that automatically boosts resolution for orography and coastline. Here is the result. The Himalayas have finer resolution. But for the rest of the group, we use very coarse resolution, 128 km, to save computational resources. We compare this customized mesh with MPAS standard 60 km to 3 km mesh. Note that the customized mesh has 120-something thousand cells, while the standard mesh has 830-something thousand cells. Here are a glance of the meshes. We look into three aspects: the mesh quality, model execution time, and forecast skills. These histograms show that the customized mesh has higher mesh quality, which means the cells generated are closer to regular hexagons. The blue bars are CPAS, and it has higher cell quality metrics. On execution time, hierarchical time stepping significantly saves computational load. You can see that we have an assignment of HTS levels for regions around Hong Kong, which is tiny, the yellow one, and the orange and green one inside. It uses small cells and small time steps. And for the rest of the world, like level 0 and level 1, the cells are large and we use large time steps. And this is the case for the standard mesh, and there are fewer HTS levels. And the execution time is shown here. The left chart is the customized mesh with HTS. The bar shows the execution time, the purple bars. And for HTS turned off, the execution time is shown in the green bars. You can see that HTS have a speed up of 2.33 times for this customized mesh. The right chart is on the standard mesh. Also, with HTS, a little bit shorter, and without HTS, the green bars are a little bit longer. The speed up is 1.2 times. And on forecast skill, we have run experiments for 3 cases, and the Taylor skill score are shown in this chart. You can see that basically the 4 cases have very similar forecast skills. The differences are tiny. Some are positive and some are negative. let me show you more details. Going back to the slides. Just pick case 1, the passage of a cold front. We evaluate against the observation data obtained from Hong Kong Airport and use our visualization system and analyze the results. For the customized mesh, this is the result of 5.5 days of simulation. The blue line is our prediction. The orange line is the observation of temperature. On the first day, our prediction is pretty good. And on the third day, it can predict the temperature drop, but unfortunately with shifting of time. And the result for the standard mesh, on the third day, it can catch the drop of temperature at perfect timing, but on the first day, the prediction is not so good. We can check the reason behind. This is a standard mesh. For this circular region, the resolution are 3 km. But for the same region, only the region in this irregular area has 3 km, 2 km, and 1 km resolution. Outside, the resolution is lower than the standard mesh. So I think that's the reason. After simulating for 3 days, and the standard mesh is more accurate, while the customized mesh is a little bit worse after 3 days of simulation with coarse resolution outside. And let me show you even some more results, not on the poster, but on the white paper. Over Hong Kong territory, there are district weather stations, 30-some in number, shown as red dots on this map. Over the Hong Kong territory, the customized mesh has 1 km resolution, shown in this figure. And for the standard mesh, the resolution is only 3 km, shown in this figure. And if we check the Taylor scale scores of the prediction of temperature over these district level weather stations, we find that the high resolution customized mesh has higher forecast skills. And let me give you some intuition. If we check the terrain data for these two mesh, you can see that the 1 km resolution has far better representation of terrain in the model. This is Tai Mo Mountain, the highest mountain in Hong Kong. And this is more detailed. And in the 3 km one, this is not so detailed. So let me give you the conclusion of this study. Customizable unstructured mesh generation is flexible. You can make a variety of meshes for specific purposes, short or long range. And hierarchical time stepping saves computational load for meshes with large resolution variation. So if time allowed, I will show you the white paper. Just go to our website. And here is a poster and slide, and here is the white paper. Okay, the contents are elaborated in text. And for our visualization system, I would like to show you. This is the CPAS cloud computing platform for simulation jobs and for you to customize your mesh. And this is the visualization. Here is a clean start. You can use this code to find the data shown as demo data, EGU2020, and this is the cold front case with HTS. And then I can show you visualization of the mesh. Just execute this piece of Python code, loading the data, the map panel comes out. You can move it to your region of interest, zoom in, and then select the number of cells to show, and then plot it. Okay, this is interactive, but for this detail, you will show, and then pause, and then you can zoom in. Okay, you see the hexagonal cells. Or you can plot the terrain data. Or by this, plot variables, terrain. Here you go. Pretty good. And then I can show the result of simulation. Run this piece of code. So again, move the map, zoom in a little bit. Choose a variable to show temperature at 2 meters high, and then this is the time slice you can visualize. The simulation starts from 5th of January and go for 5 days. So just randomly pick a time slide and then plot with the range auto adjust. And then the backend is working. And in some seconds, the results will come out. So I just show a small number of cells. So these cells are selected. You can play around to select more cells, wait for some more seconds and show again. But I skip here. And this is the piece of code I use to evaluate against the observation data downloaded as a CSV file and uploaded to the Jupyter system, and then I can run the code. It will interpolate the model results to that location, and then it shows the plotting. This is what I have shown on the slide. Thank you very much, and I encourage to ask questions, whatever you have.